Welcome, everyone. Welcome, Daniel. Welcome, all. We are going to be talking today about how to unlock a new customer base, learn how to AC couple batteries to existing solar systems. So the topic today is AC and DC coupling. Daniel, this is a NABCEP certified course. What do we want those that are here for those continuing education credits to do?
Yeah, at the end of the talk, we will have our email will pop up. Go ahead and email us with your full name, and we'll go ahead and issue those credits out.
So welcome. Let's jump into it. First off, we will be at a number of upcoming shows. Daniel, where are you going to be next?
I'll be next at the Hawaii show. This is going to be the Hawaii Solar Energy Association's hosting a solar expo. It's coming up in August. Also coming up in August is the Energy Expo down in Florida. That will be at booth 145 there. And then finally, to remind everybody, one of the largest shows in our industry is RE Plus, the main show, and that'll be in Las Vegas. We usually have free passes, expo passes for people. So if you're interested in that, email us. Again, our email will pop up at the end, and I'll make sure to get you a free pass.
Yeah, so if you're going to be at any of these shows, please do reach out. We'll have a free gift for you at the booth, and let us know. Daniel, I think that this is quite important to you, and I think it should be important to all of us that are in the solar energy industry, right? And that is to support your local organizations that are pushing for solar and batteries. Daniel, you're a member of SEIA?
Yeah, we are, and we're also a member of California Solar and Storage Association, as well as the Hawaii one as well. A lot of people might realize that the 30% residential tax credit and even the commercial one is in jeopardy right now. And one way we can help get the word out is by clicking that QR code right there, and that'll bring you to this this form, and that will give you further instructions on how to get your voice heard by Congress to keep that 30% tax credit.
Thank you for taking the time to do that if you do. The scope of today's training is going to be presented on this next slide. And essentially what we're going to do is we're going to talk about the difference between AC and DC coupling photovoltaic systems with our batteries. And really this topic, what you're going to learn, kind of extends to other batteries as well, not just ours. But we're going to give an explanation of what AC and DC coupling mean as we're using them here. We're going to highlight adding batteries and what the advantages of that are to existing AC systems. So we'll talk about what we mean by AC systems here in just a second. We'll talk about the best practices related to sizing AC coupled arrays to batteries. And there are some limitations there. We want to make sure that our batteries are capable of accepting the power that's delivered from an AC coupled array. We're also going to talk about how to use batteries to maximize solar production and really optimize that return on investment. So we'll start out at the basics. We often do. We like to start by talking about what is an energy storage system. So just at the very beginning here, an energy storage system effectively in the solar world means batteries, right? Having batteries to store that energy that's coming off of your solar array. Or even if you don't have a solar array, an energy storage system is a way to store energy coming from a generator or from the grid. So an energy storage system, as it relates to the residential market, has a number of components. One of the most important is that battery, making sure that that battery system is going to be there for a long time, making sure that it's providing a safe mechanism to store energy, making sure that it's going to provide that backup in the event of an outage. And we're showing here the Briggs Stratton stackable 6.6 kilowatt hour battery. That's a stack of 20 on the left. We're showing a single stack there of 6.6 kilowatt hours with the system. Also important to an energy storage system is an inverter capable, like the Solarc hybrid inverter there, of managing the different power sources. Now, there are many ways to do this, and it doesn't all have to be done in an all-in-one inverter like we're showing here. But having an all-in-one inverter certainly simplifies the installation process. Now, the inverter that's shown on that screen is capable of managing different power sources. And so if the grid goes down, that inverter is capable of taking power from solar to cover the loads, and if there's excess power, to charge the batteries. And then if that solar power is no longer available, the grid's still not available, using that battery power to cover the home's electrical loads. The inverter, the batteries are also capable of communicating information, and we can monitor and control that with remote apps. And additionally, if that battery gets low, we can integrate a generator and have that generator provide backup power such that the generator charges the battery, covers the home loads for a short amount of time, and then shuts itself off. And we minimize the amount of fuel use when we have energy storage. So a lot of great options. In today, we're going to be talking about micro inverters, and we're going to talk about string inverters, essentially grid-tied systems, and how we can AC couple those into in a hybrid inverter like that Solarc there, and use that AC power, convert it back to DC to charge batteries. And we're going to talk about the differences and why we might want to do that, why we might not want to do that, right? There are times when a DC system might be more efficient. There are times when an existing system is there and we don't want to have to get back up on the roof. We don't want to have to re-permit. We don't want to make a change. We just want to add batteries. We're going to show you how you can do that. So some terms we're going to be employing. Coupling in the context of PV systems. When we're using the word coupling, we mean how are we connecting it? How are solar panels coupled or connected to a battery bank? So when we're talking about AC coupled today, we mean we're going to couple the AC output of a solar array to a battery. When we're talking about DC coupling, what we're talking about is coupling DC power from a photovoltaic array through a DC input battery charger in order to charge a battery. And so in the case of AC coupling, batteries are innately DC devices. Solar panels are innately DC devices. They both have produce DC voltages, DC currents. So we're going to talk about how we have to transform that DC to AC and then back to DC if we're doing an AC coupled system. And in a DC coupled system, we'll show you some mechanisms by which the charging is regulated. And we'll talk about MPPTs and PWM charge controllers. AC coupled batteries. So some batteries have built-in AC to DC inverter converters to allow the battery to import and export AC power. Our batteries do not. We do not. We use a more efficient DC coupled battery architecture. Daniel, you brought it to my attention that some of these battery systems are also integrating MPPTs directly into the battery as well. So these are all things to keep in mind, and I'll slow it down. We'll go through the basics here. Starting off, this is at the heart of things that I like to talk about. I spent several years of my life building solar panels in a graduate research lab. And so what essentially a solar panel is it's a device, it's a semiconductor-made device with what we call a PN junction. And it's essentially an electron pump. So sunlight comes in, and that separates electrons in that PN junction from their atoms, which ends up resulting in electrons being pumped down through the solar cell. And that difference between a lack of electrons on the top and an excess of electrons on the bottom results in a voltage in a solar cell. If we start to draw those electrons off, we get a current as well. So you can think of each solar cell in a solar module as a little electron pump. It's pumping those electrons down to the backside of that cell, to the contacts that are there. And then we put a bunch of those cells in series, and the voltage of that panel therefore goes up. Each cell, when fully illuminated, is going to kick out a voltage that's specific to the material that you make that cell out of. Almost always, not always, but almost always now, the cells that we use are silicon-based cells, which results in about 0.6 volts per cell. So we string a bunch of cells together. It looks like I'm not sure exactly, but I think that's those cells that are there look like 40 cells on that solar module. And you can then approximate 40 times 0.6. That gives you a rough approximation of the open circuit voltage of a solar panel. Then we can put a number of solar panels together in series typically, and we call that a string of solar panels, and we can feed that into an inverter. Of course, we're going to talk about different ways to do that a little bit later, which we can directly transform a single solar module into an AC output. So when a solar panel is pumping electrons around, you're getting a power out of it, and that power is the product of current times voltage. If we don't draw any of those electrons, if we don't draw any current out of a cell, you have what's called an open circuit voltage, which I said is normally about 0.6 volts per cell. If you short circuit the solar cell or the solar module, you'll essentially have a lot of current but no voltage. And so we're going to talk about how to maximize the power output in this slide. So when you see a solar module on the right-hand side of the screen, you see a label like that. You see some kind of technical words at the bottom. So all technical data at standard test conditions. So standard test condition is to illuminate the solar panel at AM 1.5 conditions, which is about 1,000 watts per square meter. It's not exactly. There's about 1,000 watts per square meter of light that's passed through 1.5 atmospheres. That's what the AM 1.5 stands for. So the more atmosphere you pass through, the more the spectrum or the color of the light changes. So you probably noticed in the early morning when the sun's quite low in the sky, that sunlight looks pinker or redder. Same at sunset, and that's because you're not passing through 1.5 atmospheres. You're passing through such a low angle that you might be passing through 10, 15 atmospheres when that sun is very low in the sky. So anyway, AM 1.5 standard test conditions also specify the temperature that the cell is held at, about 25 degrees Celsius. Under those conditions, you get some output out of that cell, and the maximum power that you'll get out of a cell is rated based on those conditions. Daniel, temperature of a solar panel, normally 25 Celsius on the surface?
No, it's usually hotter than that.
Yeah, typically it's about 40, 45 Celsius. Obviously, it depends on the wind, it depends on the air temperature, etc. But we're looking at temperatures higher than that. And that's why typically you're not going to get 120 watts out of a cell, even if the sun's directly overhead. Even if you're in kind of perfect AM 1.5 conditions, typically the cell surfaces are hotter than that. Okay, so there are a number of things I want to point out on that solar module. Again, this is not a talk on solar cells, or solar panels, but the short circuit current, that's the current that you get if you short a device out. But if you're shorting a panel out, you're getting almost zero power, right? There's also a maximum power point current and a maximum power point voltage. Those are the voltages that you get when you're operating a panel where you're getting the most amount of power out. Those are typically the operational currents that you'll see and the operational voltages you'll see. The product current times voltage is what, Daniel?
Energy.
Yeah, it's power out of how much energy per unit time you're getting, how much power, right? And so current times voltage gives you power. Again, if we short a panel out, we're getting zero power because there's no voltage. If we have an open circuit condition where we have a high voltage and no current, we're again getting zero power out. So we need a device that'll maximize that power output. And there are different devices to do that.
A couple things I'm noticing on this module. One, it's a relatively small module, 120 watts. And I also see that 18 volts. That to me means it's probably a 36 cell module, which is going to be appropriate for an old 12-volt system where we might want to use a PWM charge controller, which I know you're going to talk about here in a minute.
Yeah, exactly. And so, Daniel and I wanted to share these fundamentals because, we see a lot of questions come through. And a lot of these questions have to do with things like, hey, I have a 45-volt panel. Why am I seeing 36 volts? Is there something wrong with my panel? Keep in mind that in high temperatures, that you'll see more of a voltage drop on the panels. So the voltage output of a panel will change with temperature. In cold temperature conditions, what do we see on the voltage, Daniel?
A higher voltage.
Yes, and under the current is almost proportional to the amount of light that the panel is receiving. So that current is almost a direct reflection of how much light that solar panel is absorbing. It goes up and down with the angle of the sun and with the intensity of the sun. So if there's some cloud cover, etc., you'll see the current modulating a lot. The voltage mostly changes with temperature. Okay, DC power by solar panels can be combined in a few different ways. So we mentioned the fact that when you have DC power sources, if you put them together in series, the voltage goes up, right? And the current is limited by the least producing panel in that series string. So it's also important to keep in mind that when you string panels together in series, their voltages add together. And so when their voltages add together, that you can increase them towards an upper limit. Now, typically, inverters like the solar converter have an upper limit on how much voltage they'll accept from a solar string that's coming into their MPPTs, and we'll define those in a second. But the solar inputs have an upper limit, and I believe it's 550 for a solar converter. As Daniel mentioned, on cold days, that voltage will go up. And so you do want to keep in mind if you're in a location where temperature is going to be significantly below that 25-degree standard condition, that you want to compensate for that voltage going up. So it's best not to hit that upper limit on those inputs. It's best to stay a little bit below, and you can calculate exactly how far below if you know the temperature range where you're going to be operating. We can also use DC optimizers on each of the panels. I notice in that picture we're showing on the screen, Daniel, there's a little bit of shade on those cells. Now, some cells we can have split cell panels, right? But most the panels that you're seeing on the screen, all those cells are connected in series. And so if some of those cells are not producing current, that will affect the performance of that entire module. And that entire module, if it's in a series string of panels, can affect the entire string's current, right? You're limited by the weakest link in terms of current. So one of the things you can do is you can get optimizers that can bypass panels that are not producing, at full power, and optimize that string. So DC optimizers are an option. Parallel panels also will produce that currents will add when you parallel panels. You can also parallel panels by using microinverters, and that will convert the output of each panel directly into AC. And when you're paralleling it, the currents add, and as opposed to the voltage is adding. Daniel.
One thing I've noticed on a lot of these newer modules is the number of bypass diodes. A lot of times the older panels maybe had 3. With some of these new split cell, you're seeing 6 bypass diodes. Another thing maybe to add, Nathan, is with these DC optimizers, some of them can have module level monitoring, right?
Yes, exactly. Yes. And in fact, Daniel and I, a couple of months ago, installed a system at our headquarters in Wisconsin. What did we use, Daniel?
Tigo.
Yeah, we used
TS4Os to be exact.
Yep. Yeah, and that gives you individual monitoring on each of your solar panels as well. So there's some advantages to doing that. The rapid shutdown is built into those optimizers. And so recommend considering something like that, especially if you're in a location where shading is going to be a concern. Now, this is the installation we're looking at here, the installation of microinverters directly on some Iron Ridge rail, and the panels will be mounted over top of that. Those panels will be connected into those microinverters with MC4 connectors. You can see those 2 connectors exposed on each of those microinverters. And then what's the output of these microinverters, Daniel?
240, no neutral.
Yep, 240 volt coming out of those microinverters. And so you can see what it looks like to wire those. We're looking at here DC optimizers. It looks like these are being installed on a rooftop, and that those DC optimizers that are there, as I mentioned, can correct for panels that are in shaded conditions. Now, one thing to point out is with these DC optimizers on the screen, like these Solar Edge, those that feed into a Solar Edge, these are proprietary. So to keep a live signal, the software to do that requires a Solar Edge inverter. And so for this reason, many of our installers will choose to just keep that Solar Edge inverter on the system, but bring that AC output of that inverter directly into a hybrid inverter like a Solar. Why would you want to do that? Well, these Solar Edge inverters do not support batteries. Right? They're just a grid tied inverter. And if you want batteries, you'll need to use an inverter capable of battery energy storage. Other ways to do things, we can directly connect the output of a DC solar array through a device like a PWM charge controller, that one in the top left of the screen. These are typically very inexpensive. Daniel, I've seen these things for under $20, for cheap, small PWM controllers. Now, in the top right of your screen, you're looking at a Victron unit. These are quite popular. In fact, I think the MPPT 150s from Victron are even more popular. But these devices allow communications as well. And so the MPPT is a more efficient way to get power out of your solar array. And what it does is it maximizes it varies the amount of current it draws from a solar array. And that in turn, if you draw a little less current out of a solar array, it's going to increase the voltage output of the array. But of course, drawing less current, ideally you would want to draw more current to get more power. So what it does is it adjusts the current that it pulls from that solar array up and down and gets the maximum product of current times voltage to maximize production. These can be up to 99% efficient, right? Typically, you get a little higher efficiencies when you're looking at lower power inputs to devices. Once you start powering devices near their limits, you're getting lower efficiencies due to the fact that you've got more resistive heating inside devices where the wiring is smaller. Daniel, we're showing here how a PWM controller works, right? So a PWM controller, that stands for pulse width modulation, excuse me. And pulse width modulation, what it does is it chops the signal coming out of a device to more closely approximate if you average it over time. So we're chopping this signal very fast, many times in a second. And when you do that, you're getting an average voltage. It goes up, it goes down to zero, it goes up, it goes down to zero. And by doing that, we can create a voltage closer to the voltage output that we want. These use field effect transistors to do this. It's less efficient than MPPT devices, but it's also considerably less expensive as well. Devices like VFDs, variable frequency drives, do something very similar to this, right? They're chopping up DC voltages in order to run motors, etc. So PWM controllers, these used to be quite common. Daniel, you have one of these, or you at least like this one. One of the reasons
go ahead. When I worked at Sunfrost, the refrigeration company, and we did vaccine refrigerators, we would often use these. That was maybe 15, 20 years ago. Really the MPPT charge controllers have become much less expensive. Also, by using PWM, you really need to use either 36 or 72 cell modules to get close to that voltage range of what the batteries are. Just to let everybody know, the Q&A is open for anybody. Please let us know if anybody's still using PWMs, or have you just gone over to MPPTs?
What does an MPPT charge controller do? So I've been talking about this a little bit. When you are looking at a solar panel, if you are drawing no current off of it, you're at the open circuit voltage, the bottom right side of the graph that you can see on the screen. Once you start drawing current off of that panel, you're now producing some amount of power. If you draw more current off that panel, you'll see the voltage will drop. And so we're moving along. The more current I draw, the lower the voltage becomes on this graph. So the voltage is on the horizontal graph, the current is on the vertical graph. And so if I draw a lot of current, eventually we get to this place where we call it the knee of a curve. And I generated a large number of these curves during graduate school. And what these curves do is the place where you can draw the largest square under that curve, or the largest rectangle, the most amount of area under the curve, that's the maximum power point. And the power here is indicated by this blue curve. You can see when you're drawing a lot of current up here and have very little voltage, you have almost no power. But as you decrease that current just a little bit, that voltage comes up, and eventually you get to a spot where you decrease the current just enough that you're getting a maximum product of current times voltage. So what these MPPTs do is essentially just vary forward and back the amount of current they're drawing, up and down, I guess. And that changes voltage and current at the same time. And we're looking for that maximum power point, that P max. So when you're looking at IMP and VMP, those are the current at maximum power point and the voltage at maximum power point as tested under AM 1.5 conditions. Now, those, of course, vary throughout the day. That's when you're fully illuminated by sunlight, at 1,000 watts per square meter. Well, if the sunlight comes at an angle, you'll get less current, etc. And so this varies throughout the day and throughout cloud conditions, throughout angle of the sun, etc. And so these devices continuously adjust the current and produce a maximum power output. And so they do that all day long, and you can get very efficient power outputs from your solar array, as long as that solar power is somewhere to go, right? We often mention that, Daniel. If your batteries are full and you've got an off-grid system, you don't have to pull any loads off of it. Your solar array will be producing zero power, right? Electricity needs somewhere to go. Well, the Solarc that you can see on the screen there, that's got built-in MPPTs, right, Daniel? And I believe that's a 15K, and that has 3 independent MPPTs built into it, each one capable of 7.5 kilowatts of power. Now, the full output power of the Solarc, or full input from solar, will be limited to 15K. That's the nameplate rating on the inverter. But you can oversize your solar arrays. And you can oversize those solar arrays so that you get something called inverter clipping, right? Which will allow you to pull 15 kilowatts earlier in the day, etc. So anyway, the Solarc has these built in. Here's an example where we've got a solar array coming directly into an MPPT. And this system is coming into a combiner. We're showing a class T power in. And that's coming out and going to a Victron Quattro inverter. This inverter is capable of outputting that DC power into the loads. It's also capable of connecting with a grid. So it does not have the MPPT built into it, but that inverter is capable of a grid interface. Daniel, is this an AC or a DC coupled system?
This is a DC coupled system.
Yes, so the DC from the solar goes into an MPPT. It remains DC, but it's regulated in terms of a maximum output power, and that MPPT then provides the appropriate charging voltage to charge the batteries. So everything stays DC between the solar panels and the battery charging, right? So between the solar panels and the battery, everything is DC. So this is a DC coupled system. Here's another example of a DC coupled Solarc. These are rapid shutdown devices. If you have a rooftop solar array, you're going to be required to have a rapid shutdown device, and that's for safety reasons. So if you depress this red button, these are essentially switches that open up and shut the solar output down at the panel level. We bring these in as DC into the MPPTs of the Solarc. The Solarc then can use that energy to either power loads, charge the batteries, or send that excess power back out to the grid through the load center. And we're also showing that this inverter can integrate a generator, right? So we're showing here that we've got a generator with a 2-wire signal to start. And so in a grid outage, this inverter, if there is no solar power and the battery state of charge is getting low, this inverter can start up a generator, cover the loads, and charge the batteries. So it is worth noting that this is a little bit dated. We're looking at information from 5.5 years ago here, but 80% of the U.S. market was controlled by essentially Enphase and SolarEdge inverters. Now that's certainly changed with Tesla entering the game and with other companies entering the game. But at this point in time, 5 years ago, 95% of the world global inverter market was made up by these two. So there are a very large number of systems out here which are AC coupled or essentially grid tied systems. What do we mean by grid tied, Daniel?
That means that they don't work if the grid isn't there. And I was always surprised, Nathan, how many people, when they were sold a system, didn't understand that concept.
Yeah, they thought,
So
well, I
right,
have solar power. If the grid's down, I have solar power, right? But that's not the case, right? These are grid following inverters. Um, and so we can't keep that power alive unless we have a system like the Solarc here. Daniel, what's different about the Solarc? Is it grid following? Is it grid forming? What is it?
grid following, right? So what we need is a solar to form a grid so that the solar edge or N-phase micro or string inverters will think that nothing's different and grid is still there and they'll continue to output.
Yeah, so the Solarc inverter can be grid following and it can be also grid forming, right? And so in the event of a grid down situation, that Solarc inverter can form a grid using power from the batteries, and those and that formed grid can then be latched onto by those string inverters. So you can see here on the screen, we've got a couple of solar edge inverters, probably had a rooftop solar array that they didn't want to get back on the roof and rewire. And so we're AC coupling these two inverters, probably two 20 amp inverters, right, into the Solarc through the generator port. And now if the grid goes down, they do have this solar power. This solar power is kept alive by the Solarc inverter. We also have batteries to back up their loads. And so in a grid down situation, this system has backup power. And so some advantages to doing it. This is called the AC coupling of string inverters. We can also do this with an N-phase based system. This is a very common type of solar array. So a solar array with a grid tied solar array with, those are called microinverters, Daniel.
Yep, those are probably IQ7s,
Mm-hmm.
but they, have gone on to the IQ8s at this point.
Yeah, and these microinverters, these IQ7s, IQ7 pluses, I think I can read on the screen there, but these IQ7 pluses are mounted a single inverter to each panel, right? And so we're mounting on each panel, we're mounting a little microinverter. It's a grid following inverter. And as long as the grid is up, these microinverters will kick out as much power as they can from the solar panel by essentially maximizing the power point, just like an MPPT does, but outputting it as AC, 240 volts AC. And that power is then sent back through this N-phase combiner panel and into the load center of the house. And if you're not using all that load, then you're sending that excess power back to the grid. Now, in states where you have net metering agreements, this can be a nice way to, you don't get backup power with this, but it can be a nice way to tie your solar array in. We've lost net metering out here. Daniel, you do a really nice talk on NEM 3.0, which is very much not NEM 3.0, right? It's not net energy metering anymore in California. It's net billing tariff. And so it financially is no longer advantageous to do this kind of a system in many locations, not just California. If that customer wants backup power, if they want batteries, or if their NEM status is expiring, you have this option to come in and AC couple the output of those microinverters to a battery. So we can use these microinverters to charge a battery by bringing it through a hybrid inverter like that Solarc that's shown on the screen. Now, this is a smaller Solarc. I think we're looking at an 8K here. It has a 60 amp pass through, and we will typically back up critical loads with this one. We could, of course, use a 15K to back up the whole home. But you can see there's still that rapid shutdown button that's there. When you push that rapid shutdown button, it will shut the full system down. And this is an example of a simple AC coupled microinverter array tied through a Solarc to batteries.
One interesting thing on this slide, Nathan, is that we are potentially not only taking 60 amps from the grid, but we could push 60 amps back into that load center. And a lot of times these panels are 200 amps with a 200 amp bus. And with the 120% rule out of the NEC, usually it's a 40 amp breaker, unless you derate the main maybe, or upgrade to a 225 bus bar. What's interesting about a lot of these newer inverters is the PCS control, or the ability so that it can always draw 60 amps, but using the controls inside the inverter, it will never send back more than 40 amps, so you don't overload that bus bar.
Yeah, and that's a great point, Daniel. I mean, assuming that this initial installation was done properly, right, you would not be able to exceed on a typical 200 amp service panel, as Daniel was talking about. You would not be able to exceed 40 amps of backfeed current unless you, as he said, derated the main or upgraded the panel to having a larger bus, right, a bus capable of sending more back. But because we have PCS control in the Solarc, you can always set a limit on that, which can avoid a costly panel upgrade, right? Okay, here's an example where we're looking at a larger overall system, and this system is showing both AC and DC coupled solar, right? We've got a microinverter array on the roof. I can think of an example in my mind where somebody had this. They had about a 40 amp maximum array on the roof, and it wasn't quite enough to feed all the power, right? And so they wanted to add another solar array, but they also wanted batteries at their location. And so what they did is they kept that AC coupled array. They fed that in through the generator port on the Solarc, but they also brought in, through the Solarc has direct connections for DC solar as well. They also brought in a new solar array to bring more power in, and they DC coupled it, which is more efficient, right? So if you're DC coupling solar, you're taking the DC output of a solar array, feeding it through an MPPT, and going to the DC input of a battery. Instead of each time you convert between AC and DC, you lose some percentage. And so keep that in mind. You know, if you're doing an AC coupled array, you're already going to lose some percentage in terms of round trip efficiency when you're charging your batteries up. A DC array is more efficient. So you can absolutely do both. With the Solarc 15K, you can bring in up to 19 kilowatts of AC coupled solar, 19.2. And on the DC side of things, you can bring in an additional 15 kilowatts of continuous DC power in. Now, there are some limitations when you're doing both, but the AC limitation is really occurring from the AC bus of the inverter, and the DC limitation is occurring on the DC side of the inverter. So they're somewhat independent of each other. Of course, when you're coupling to loads, you have to pay attention because you would be using the AC bus with the DC side. So I think the limitation is somewhere around 30 kilowatts of combined AC and DC solar power for these inverters. So in a grid down situation, the AC solar is kept alive. So even though the grid goes down, the batteries can be used. The solar that's there can be used to grid form. So that Solarc inverter in a grid down situation no longer is grid following, it's grid forming. And it can form a grid that the AC coupled solar can latch onto and provide power to. And so you're able to keep both arrays alive in a grid down situation. Daniel, what are we looking at here?
The single line diagram, again, we have a Solarc 15K here with the 200 amps coming in, 200 amps going back out to that main panel, the home loads. We have our AC coupled solar here. We don't have any DC coupled solar in this example here. We got a single stack of 3 6.6 batteries, bringing the power over into the Solarc.
Yeah, and so we're recommending some wire sizes. Of course, the lengths of your wire runs can influence this, but to try to give you a simple idea of what an AC coupled system looks like with the Solarc 15K here. Daniel, we're looking here at bringing that AC coupled array. This is the single line diagram or multi-line diagram coming from the Solarc manual itself. And we're showing bringing those AC coupled inverters in through the generator port of a Solarc. It's worth keeping in mind here that if we also want to tie a generator in, we don't have the generator port available now. So we're going to talk to you later about the ability to still use AC coupled solar and a generator at the same time. There are also communication lines that are shown here. And it's important to keep in mind that our batteries can communicate directly with that Solarc as well. We're looking at the inside of a Solarc 15K here, and just going to point out a few things. We've talked about MPPTs, so hopefully you can see my mouse on your screen. I'm highlighting the DC input for solar there on the screen. So the MPPTs are there with those orange cam lock levers that you can see. And then the AC solar would come in through L1 and L2 on the generator port, the neutral bars down here at the bottom. If you are using AC coupled solar, you will want to have the CTs installed. The CTs get installed on the communications hub in that solar converter. So on that comms bar there, 3, 4, 5, and 6 are CTs. Daniel, what is a CT?
A device that can measure current flowing through a wire, I believe by the magnetic field it generates, without actually having to touch the wire. Again,
Yeah,
amps,
so
not volts.
exactly. So a CT is a current transformer, and it does exactly what Daniel's saying. It essentially it looks at the induction that's happening through that wire in a number of coils, and those coils provide an output voltage, and that output voltage can signal how much AC current is passing through the CT. Those get wired into 3, 4, 5, and 6. B and B are also highlighted. They're in positions 11 and 12. That is for your rapid shutdown device, right? So code is going to require you to have an accessible disconnect on the system, which will shut that system down from the outside in the event of an emergency. So that's your emergency stop button. We mentioned that our batteries communicate with the Solarc. The 6.6 battery communication wiring is showing here. It's a fairly simple connection. If you're using our Energy Track gateway in order to monitor individual battery modules, you would connect that through the RS45 port. So we just have 2 RJ45 connections. That's an Ethernet sized connection. And then that CAN bus port on the battery controller, that will come through a dongle and go directly into the Solarc. And that dongle is provided with that controller, comes in a bag inside that controller box. And so it's fairly easy wiring. It's just a direct connection into the Solarc battery communications port there. If you've got multiple stacks of batteries, you can parallel these batteries, and you just need a single one of those batteries controllers to connect directly to the Solarc. If you are using our Energy Track gateway, you can connect it to the first RS45 port. Or if you're not, you could just put a terminating resistor in that first connection. We always want to have a CAN bus chain is expecting a big loop, and you need to tell that the computers on that chain where the last battery is. And so either we use the gateway, which has a built-in terminating resistor in this dongle, or we put a terminating resistor in that.
Nathan, we have a question.
Sure.
What is the maximum number of 6.6 batteries that can be coupled or put together?
We can put up to 18 of the modules together, right? So that's 6 stacks of 3. So we can do 6 stacks. That's 120 kilowatt hours. Now, keep in mind that you may be limited by other codes and regulations. If you're in a garage, for instance, you may be limited to 4 stacks or 80 kilowatt hours. So good question. Thank you for asking. Let's look at the initial setup. So if you are using a Solarc, the initial setup on the Solarc, you'll want to go into the settings. Now, you can do this off the front screen, or you can do this through the app. I think a lot of people are now programming through the app, but we're going to show you how to do it through the front screen as well. So one of the first things, it's an important thing, is the first time you energize the DC bus, you're going to want to make sure that when you turn that inverter on, and I think it's a good idea to turn it on with battery power, grid power if it's available, but you have to make sure you check this box for activate BMS lithium batteries. So that BMS lithium battery 00 box should be checked. And if that's checked, the inverter knows that it should be communicating on a CAN bus channel with the battery. Doing so should get you some automatic settings. So it should automatically communicate that there's a certain number of amp hours inside the battery. So for a single stack, you'll see that appear as 398. The maximum charge rate, this is a global maximum charge rate under that first battery charge. What do I mean by global, Daniel?
That means it can come from any source.
Yeah, from all the sources combined, we will not exceed this programmable value. Now, you can program that to whatever you like. The recommended maximum continuous charge and discharge ratings come in a table in the 6.6 battery manual. It's 195 for a single stack, and the maximum discharge is 273 for a single stack. Though I will point out, if you're using a Solec 15K, the Solec 15K is only capable of 250. So the batteries are capable of a little bit more there. At 48 volts, Solec 15K will be limited to 250. On the charge tab inside of a Solarc, you will have the option to enable generator charging with this checkbox here, and then this column. This column is related to the maximum DC charging rate. So I do want to point that out. When we have 60 amps DC in that 60 amps in that column, it's referring to the charging rate of the batteries. The batteries are at a nominal 48 volts DC, so that's 60 amps of DC charging. You can also check this box for charging if you have something connected to the grid. So if you have a system where the utility is connected to the grid port, 100 amps could be pulled from the utility during a charge cycle. That's the maximum value it'll pull from utility. If you have both batteries and grid charging at this, or both solar and grid charging at the same time, it would default to this maximum global charge limit that we mentioned earlier. Okay, on the discharge side of things, the 6.6 batteries are going to choose to operate in percentage mode by default. And you can set a shutdown, a low battery, and a restart percentage. The shutdown voltage is the voltage, or percentage is the percentage at which the batteries reach that the inverter cuts off loads if it's operating off batteries where no grid is present. The low battery value that you can see here, 20% as set on the screen, that's going to alert you that your battery is low. The Solarc will beep at you if you've got beep enabled to just let you know, hey, you're getting towards a low battery situation. And the restart percentage here is a percentage at which, if you're in a grid down situation and the batteries have reached the low battery shutdown voltage or shutdown percentage and shut off loads, they have to be able to charge back to a certain point. So if they're charging back off of solar, we're not going to turn it on immediately when we hit 10%. And we're going to turn it on when we hit this restart percentage. And now, depending on how big your solar array is, you might want to charge those batteries up more before you turn the loads back on, so you don't have the loads turning on and off multiple times in a day. And then the battery empty voltage, that's a reference point at which the battery is considered empty from the battery perspective. For a 6.6 battery, that should be set at 48 volts. What about for AC coupling? How would we program a Solarc to let it know that we've got AC coupled PV coming in through the generator port and not a generator? Daniel, what are the things that we should be doing for AC coupled PV in the smart load settings?
Well, we want to make sure we check for AC coupled input to the generator. Make sure that we have grid cell enabled, and then we're going to set some of those smart load off and on tabs right here. And so, Nathan, you had mentioned that the Solarc is a grid forming. Does it adjust the grid? Does it form maybe a different frequency? I'm kind of leading you here with this question.
Yeah, exactly. Yeah, so it's a great question. So what do we do? A AC coupled grid composed of IQ 7 pluses, like we were looking at earlier, right, is going to produce as much AC power as possible and try to feed it back to the grid. Well, if the Solarc is the grid, if the Solarc has formed the grid, then those microinverters might be producing more power than the home is consuming. They might be producing more power than the batteries want. And so one of the things that the Solarc can do is it can turn off the AC microinverters and adjust their output rate by adjusting the frequency. We call that frequency shifting. Another thing that we can do with the Solarc is have it completely turn off battery charging when that battery gets full. And so notice that anytime the batteries are above 90% with this setting would then turn off battery charging from that smart loads. And the way it does that is it cuts the gen port off. The power coming in from the microinverters gets cut completely. If the batteries then drop below 80%, it turns it back on, so those batteries start charging from those microinverters. as Daniel was leading to earlier, we can slow down or speed up the power output coming from the microinverters, or increase/decrease the power output of the microinverter array by doing what's called frequency shifting. So the solar converter can frequency shift. If you get above 62 hertz on a 1741 SB microinverter, it's going to turn off. And so by adjusting that frequency towards 62 hertz, it will reduce the power output of the microinverter. And I don't know the exact, Daniel, do you have that memorized? The exact power output? Is it at 61 hertz, it drops it to 50%?
I don't have it memorized.
Okay, but that's essentially what that solar converter can do. It can, because it's no longer tied to a real grid, it's grid forming, it can adjust the frequency to slow down those microinverters. Now, if we have a microinverter array, we might also want to have a generator. Now, let's just look at a simple example of using a generator with a solar. We can use a generator on the gen port of a solar if we don't have AC coupled solar, but we could also use a generator on the grid port of a solar. And Daniel and I often prefer this method of installing generators using the grid port. Certainly for off-grid, they even recommend this. But we prefer this because it leaves the generator port open either for AC coupled solar or for smart loads. Additionally, you're no longer limited to the 80 amps of continuous AC power of the gen port. You can have 200 amps from your generator. Now, our 26K generator can be brought in through a transfer switch into the grid port on the Solarc 15K, and that leaves that generator port open. The Solarc can still use a two-wire signal to start and stop the generator. It's going to run off of batteries first, and if the batteries get low, it can send that two-wire signal to start. So you don't lose that ability just by putting it on a transfer switch. But it also leaves that AC coupled, the generator port there for AC coupled solar. Now, Daniel, what am I showing on the screen? I've got a Symphony 2 50 amp line voltage lockout module. What is that for?
So when the generator is running, the Solarc is no longer grid forming, it's grid following. It's following the grid, the signals generated by the generator. And that kind of eliminates our ability to do what you were referring to, the frequency shifting to shut off those AC coupled solar modules. So what we need to do now is have a physical disconnect to prevent those AC coupled microinverters or string inverters from backfeeding the generator.
Yeah, we don't want the power of those AC microinverters going into the alternator, the generator, right? If the generator is running and there's not much power being drawn by the loads of the house and the AC coupled solar is feeding back in, they could backfeed the generator and ruin the generator. So by installing a $100 Symphony 2 line voltage module, we can turn off that solar whenever that generator is powered up. Now, keep in mind that generator is not going to be running long, and it typically is only running when there's not enough solar to keep up with the loads. So it's not like you're losing a lot of solar. When that generator starts up, it starts up because the batteries are low and the AC coupled solar was not covering the home's loads and not charging the batteries. Now, I mentioned that you can still use a two-wire signal to start, regardless of whether that generator is on the grid port or on the gen port. We're going to use pins 7 and 8 for the dry contactor to feed into the two-wire signal to start of the generator. So dry contactor essentially is exactly what it sounds like. It does not produce any power output. It's just either pins 7 and 8 are either connected to each other or disconnected to each other inside that Solarc. And so it'll either pass current through a loop or it won't. So that dry contactor can be wired into pins 4 and 5 on either our 26K or our 13K generator that you can see there, or any of our two-wire start generators. And that'll allow the inverter control of that generator. We do need to disable something though, Daniel, right? What do we have to disable on our generator in order to use two-wire signal start?
Yeah, so our generators are grid sensing. So they're looking for grid, and if grid goes away, they're going to start up. The grid flowing to the generator not only is used for grid sensing, but also keep the starting battery, any battery warmers charged up. So what we need to do is tell the generator that even if it still sees grid, because you're probably going to want to feed that off the backed up loads panel, still start if you see that 2-wire signal to start.
Yes, exactly. So we're going to disable the auto main sensing. The instructions are on the screen there. As well, you're going to tell the inverter that you've got a generator on the utility port, the grid port, and then we can set up our charging rate there. And one thing to keep in mind about your charging rate is when you're charging off a generator, when you're running a generator, the generator has two jobs. One job is to cover the loads of the inverter, because the inverter is not producing power from the batteries now, it's charging the batteries. So the generator has to cover the loads of the home and have enough available power. So if you have a smaller generator, keep this in mind, to also charge the battery at the rate you're specifying. So 100 amps at about, let's say we're charging at 56 volts. 100 amps at 56 volts is 5.6 kilowatts of power going to the batteries. If you've got a smaller generator, make sure you've got enough power left over to cover the home loads. Otherwise, you might have the generator shutting down. We're almost out of time here at the top of the hour. Feel free to continue to drop questions into the Q&A. We're going to highlight a little bit the 6.6 stackable battery that we have. One of the things that we really like about this battery is how quickly it installs, but it also has some pretty great performing specs. The battery can be discharged to 100% depth of discharge. It can be discharged and charged quite quickly. It can be charged at 0.75 charge rate, which that means that in an hour and 20 minutes. So the C rate here is 0.75. And that means in an hour and 20 minutes, we can charge this battery from 0% up to 100%. So fast ratings on that. Uses superior LFP chemistry. We've been developing intellectual property on LFP battery chemistry since 2010. And I know the industry has moved our direction on this, but for 15 years, we've been kind of perfecting LFP battery chemistry. You're looking at the power output ratings for this battery. A single 6.65 kilowatt hour battery has a power output rated at 1C at 6.6 kilowatts. There are some reductions that occur from the battery controller and our need to keep the batteries balanced in terms of power output. But a two stack of batteries can output 10.6 kilowatts of power. So a lot of good power output there. 14 kilowatts of power output can come out of a three stack of batteries. It's notable that can cover the 12 kilowatts needed by a Solarc 15K. And then we've got larger battery stacks. Overall, we can go up to 120 kilowatt hours of power output. These are all 48 volt batteries. We don't make this in another option. But Daniel, we do have an option for 24 volt systems for people that have some legacy systems, right?
Yep, our 5 battery on the far left there is still available in 24 volts. Nathan, we're talking a lot about specs and stacking batteries, but I think what also sets us apart a lot of ways is our company. Briggs Stratton is a 100-plus-year-old company. We have a lot of resources, and so there's a lot of stacking batteries on the market, but we're going to be around to see our warranties through. We're here with our tech support, which is very responsive. Nathan and I can always be leveraged for any of your systems, as well as the salespeople. So it's not just the products and the technology, but it's also the people and the company you deal with. So I want to just highlight that and mention that's one of our strengths as well.
Yeah, I appreciate that, Daniel. And unlike a lot of the competition that's out there, we don't have a throughput limit on our warranty. It's a 10-year warranty on our batteries, right? And we don't have a throughput clause that says you can't put more, you can't charge or discharge more than a certain amount. So it's a full 10-year warranty on that battery. 15-year warranty, notably on the Amplify battery that's there. It also has closed loop communications with the Solarc. You can build large systems with that as well. And if you're new to commercial, we have high voltage battery modules as well. Our server rack mounted battery is shown on the right side of the screen. We can go up to 1200 volts with those systems. So if you're interested in a design like the one you see on the screen for our commercial offerings, reach out and we can connect you with our commercial team that can do high voltage batteries for you. Again, still using safe LFP chemistry. Yeah, reach out if you want to learn more. There's a QR code there on the screen. We also encourage the use of monitoring your systems. One of the reasons for having closed loop communications is you can check how your system's doing remotely. Solarc offers a nice option with that. It also gives us the ability to help you out remotely, right? So Daniel, you mentioned our tech support team. Our tech support team has a lot of knowledge about Solarc systems, and if you need our help, you can reach out to us on that. You are looking at a system here showing power production. You can look at the battery state of charge. A lot of information about your battery can be seen within the Solarc app itself. Here's an example on the screen where you can see battery information from our communicating batteries on that Solarc screen, including things like battery temperature, etc. Now, this is an aggregated view of the battery. And it's a little bit different that, if you use our monitoring platform, not only can you see that aggregated battery view, but you can get individual battery monitoring as well, together with alerts and other things. So we do offer an energy track platform to monitor batteries too. Daniel, what is our IQ program?
So our IQ installer program is open to any companies that have installed at least one of our batteries. And what we'll do is we'll give you, right now we're running a special promotion for $150 per battery and $1,000 off that first install. So go ahead and apply. There's a link there. And then when you get that first one done, we'll give you $1,000 and then $150 for every battery. So if you do a 3-stack, I would give you $1,450 back.
Great. And it also allows us to put you on our map. It allows us to direct customers your direction. We often tap our IQ installers when we're doing beta test programs, etc. So we encourage you to join. If you're interested in signing up, you can reach out. We will be sending out these slides in a follow-up email. So please, you can also use that QR code on the screen. So please reach out if this is something you're interested in.
Additional benefits, Nathan, as well, is trip charge reimbursements. If you're going out there, referrals. We'll also send you out a free swag pack as well on co-marketing opportunities. So again, this program is really designed to elevate both you and again, these are manufacturer's rebates. So all you do is upload the proof of purchase from your distributor, and then go ahead and apply. And the $150 runs through the end of August. The $100 one is kind of going to be after August. So every battery is $100 off.
Yeah, and that's as long as you're part of the program, right? And these get paid out, I believe it's quarterly. You get a check in the mail for those batteries that you install. So a lot of benefits to that. Now, those of you that are here for those NABCEP continuing education credits, sorry, we're a couple of minutes over. Do send an email to us, as your name should appear on the NABCEP certificate. Do you want to be consistent with that? Energy storage training at basco.com. That's Briggs Stratton Company.com. Energy storage training at basco.com. Let us know how your name should appear on that certificate. We'll get those issued. So thank you for attending, everyone. And Daniel, are there any last questions?
None I see. If anyone has questions, go ahead and email us, call our application engineers, and we'll help you out.
All right. Thank you, everyone. Have a great day.